prove this theorem on simultaneous diagonalization. We'll first prove the backward direction, which is easier. Now we assume that F is a simultaneously diagonalizable family. How do we want to prove that F is a commuting family? So for any A, B in F, because A and B are simultaneously diagonalizable, there exists an invertible S such that S inverse AS is equal to this diagonal matrix and S inverse BS is equal to another diagonal matrix. Then, if you look at those two matrices, which are diagonal matrices, they are clearly commuting with each other. So, S inverse AS times S inverse BS is equal to the multiplication in the other way. And this, when you simplify it, they cancel this S with S inverse. You have AB equal to BA. So F is a commuting family. This proves the backward direction. For the forward direction, so now we assume F is a commuting family. And we will prove that F is a simultaneously diagonalizable family by induction. Induction on the sides of the matrix N. If N is equal to 1, then every matrix is a scalar matrix, and there's nothing to prove. And I assume that now N is greater or equal to 2, and that for each k equal to 1, 2 through n minus 1, any commuting family of k by k diagonalizable matrices is simultaneously diagonalizable. So this is our induction hypothesis. And now let's see how to deal with the case when k is equal to n. First, there's a trivial case that we want to exclude. If every matrix in script F is a scalar matrix with the form lambda times I, then there's nothing to prove. because those matrices are already diagonalized. So we may assume that there exists A in F with K, which is greater or equal to too many distinct eigenvalues. Because each matrix is in F, which is a family of n by n diagonalizable matrices, this matrix already has n minus eigenvalues. And if the first case fails, then there must exist an A in F with at least two distinct eigenvalues, say k distinct eigenvalues, denoted lambda 1 through lambda k. Since A is diagonalizable, by assumption, on F, there exists S sub A that is non-singular, such that SA inverse times A times SA has the following form: lambda 1 times in1 through lambda k ink, with n1 plus plus nk equal to n. Now, for any B in F, since by assumption that A commutes with B, we have, by inserting this S of A, the following equation. And we denote this equation by star. And now we claim that S A inverse times B times SA is block diagonal with k blocks, where B sub I is an n sub I by n sub I matrix. It should be hard for you to prove this. I'll let you think about it for a while, and then I'll tell you the proof later. Indeed, if you assume that SA inverse B SA has the following block form, where B sub ij is an ni by nj matrix. Remember, n1 plus n2 plus nk is equal to n. Then it follows from the star equation, which is due to the commutativity of A and B. The star is same as saying, so if you look at the product of this guy with this diagonal form as a inverse A SA, you will get the following equation. By comparing the block entries of both sides, you get lambda I minus lambda j times bij equal to 0 for any I not equal to j. And because at the beginning we assumed lambda 1 through lambda k are distinct eigenvalues of A, so this guy is non-zero. And therefore bij is equal to 0 for any I not equal to j. So this verifies this claim. Moreover, since B is in F, and F is a family of diagonalizable matrices, this S inverse B SA is also diagonalizable. And by our lemma, we have B sub II is diagonalizable for each I greater or equal to 1 less than or equal to k. Remember, our lemma says if you have a block diagonal matrix that is diagonalizable, then each block is diagonalizable. So we have B sub II diagonalizable. And furthermore, that F being assumed to be a commuting family will imply that those little matrices, as in the blocks of SA inverse BSA, will also form a commuting family in their respective spaces. Let me make this more specific. For any B prime in F, remember we have BB prime equal to B prime B by assumption, which implies that as the inverse BSA commutes with as the inverse B prime SA. By what we just proved, this guy has this block diagonal form. And similarly, you have this guy also takes a block diagonal form. Say B11 prime through BKK prime. That those two guys commute with each other will imply the corresponding little blocks commute with each other. So this tells you that BII commutes with BII prime for any I greater or equal to 1 less than or equal to k. Now, applying the induction hypothesis to n sub 1 through n sub k, remember the assumption here that n sub 1 through n sub k must be strictly smaller than the size of this matrix n. Otherwise, this will be boiled down to the first trivial case. So those k integers must be strictly less than n. We have there exists T1 in GL N1 F and TK in GL NKF, all non-singular matrices, such that Ti inverse times Bii times Ti is a diagonal matrix of size n sub I by n sub I for all I greater or equal to 1 less than or equal to k. And all be in script f. And now we can finish the proof. Now let S be SA times this block diagonal matrix T1 through Tk. Then we have S inverse Bs is diagonal for any B in F, which proves that F is a simultaneously diagonalized family. And this finishes the proof.